So in this video, we're going to talk about how to represent a given series or summation using sigma notation. So remember from the previous video, a series is just going to be the sum of some numbers in a sequence. And usually the sequence will have some discoverable pattern or rule that governs the generation of the elements in the sequence. So for example, for the series 0 plus 2 plus 4 plus 6, or the sum 0 plus 2 plus 4 plus 6, that comes from adding the elements in the sequence 0, 2, 4, 6. And typically when we're given a series or a sequence, there's going to be some discoverable pattern that the sequence or series is following. So for an example, in this case, what I want to recognize is that 0 is the same as 0 times 2. 2 is the same as 1 times 2. 4 is the same as 2 times 2. And 6 is the same as 2 times 3. So there's a pattern where we start with a lower index and an upper index, and we multiply 2 by the incrementing index value. So for example, I could represent this particular series here, 0 plus 2 plus 4. I said plus but didn't write it. 0 plus 2 plus 4 plus 6, which is the same as 0 times 2 plus 1 times 2 plus 2 times 2 plus 3 times 2. We could represent that using sigma notation by saying, hey, I'm going to start at 0 and I'm going to increment my way one at a time through the number 3. So I'm going to start at I equals 0, incrementing through the number 3. So there's going to be 4 terms. And then I see that 2 shows up each time, being multiplied by the numbers that are being incremented. So I could replace the numbers that are being incremented from 0 through 3 with the letter I. I could say, hey, I'm going to generate this series by taking the sum from I equals 0 to 3 of 2 times I. So I want to first discover what is the pattern governing the sequence, or the pattern governing the generating of the series, and then try to write it compactly in sigma notation. So right here, what we see is the other possibility. So a series or sequence can be finite. In this case, it's finite because there are only 4 terms. Or a series or sequence can be infinite. And this one I know is infinite because it's plus dot dot dot, and there's no endpoint on this, saying that it's saying to me discover the pattern and then continue that pattern infinitely or forever. So the same sequence, if I have 0 plus 2 plus 4 plus 6, I should have put a plus 6 in there too because that's what I wanted, but I put plus dot dot dot. Now I have an infinite series. So this is going to equal, just like before, it's going to be 0 times 2 plus, it's going to be 1 times 2 plus 2 times 2, and then the 6 is going to be plus 3 times 2, but it's plus dot 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 now. So if I represent this using sigma notation, I'm going to say, hey, I'm incrementing starting at 0. So I'm going to go from I equal 0, but it doesn't stop. So it's going to go from 0 to infinity, but the pattern is still going to be multiply 2 times the index I. So this is an infinite series. This is a finite series. So another example, so I have the square root of 1 plus the square root of 2 plus the square root of 3 plus the square root of 4. So we see that we're incrementing the numbers 1. We're incrementing starting at 1 all the way through the number 4. So the pattern here hopefully is fairly obvious. This is the sum of I equal 1. We start at 1 and increment 1 to 2, 2 to 3, 3 to 4. So go from I equal 1 to 4 of the square root of I is going to generate this 4-term series right here. So here we change things up just a little bit. We have the same series, essentially, except we're going out further. So usually a series, what's going to happen is they're going to give you enough information so that they think you can identify what the pattern is. And then you might be told where you should end the pattern, because the writer doesn't want to write the square root of 5 plus the square root of 6 plus the square root of 7 all the way out through the square root of 27. So this one would be essentially the same as the other, except now it's still starting at 1 and incrementing its way, but now it's incrementing its way all the way out to 27, so it's still going to be the square root of I. If I don't want to know up front, or if I don't know up front what this last number is going to be, I might say end when you get to the number n. So increment 4 to 5, 5 to 6, 6 to 7, all the way out until you get to the integer n, and then stop. So this again would be the same series, but this would be the series from I equal 1 to stop when you get to n. We don't necessarily want to know ahead of time where we're going to start, or stop, I mean. So there's that series. And then here, if we shave off that end piece, this is an infinite series. So we would simply say, hey, the pattern is start at 1, increment, starting at 1. So we're incrementing and generating all of the natural numbers, 1, 2, 3, 4, 5. But we're not stopping anywhere. So this would be the sum from I equal 1 to n, sorry, not n, but to infinity, because we're not stopping, of the square root of I. So again, the idea is to identify the pattern, and then you have to decide where is the pattern ending? Where is this upper bound of summation going to happen? And how do I represent that upper bound of summation? So here I have another one, and this one is chosen to identify that sometimes what we need to do is rewrite a series so that we can try to see what the pattern is. So in this case, what I want to recognize is that underneath the radical sign, whereas before we were incrementing by 1, now we're incrementing by powers of 2. So in this case, 1, we want to recognize is the same as 2 to the 0th power plus the square root of 2, but 2 is just the same as 2 to the 1st power. And this is common. So being able to understand that 1 can be written as a positive base to the 0 is important. That shows up quite a bit, and sometimes it's important to write things that way. Sometimes you'll get a number 1, but you'll want to be able to write it, for example, as a fraction that has a denominator that isn't a 1. So we have to be when we see the number 1, we want it to be flexible in how we visualize the number 1 and understand there are different ways of writing that number. So I want to recognize I have powers of 2. This is plus the square root of 4, but 4 is just 2 squared, plus 8 is under the radical sign, but 8 is 2 cubed. And then hopefully this is enough to see the pattern. That's at this point 16 is 2 to the 4th power plus ... and then 64 we need to figure out, well, what power is that? And then that's going to be 2 to the, see if 2 to the 4th is 16, and 16 times 4 is 64. We'll need to multiply this by 2 squared, so it looks like we're going to get 2 to the 6th. And then you just kind of want to check your work. What's 2 cubed? 2 times 2 is 4 times 2 is 8. And 8 times 8 is 64, so definitely 2 to the 6th power. And then you can see the number that's being incremented is in the exponent position. So we're starting at 1, and we're incrementing from 0 to 1, 1 to 2, 2 to 3, 3 to 4, all the way out to the number 6. So to represent this in summation notation, I'm going to start, and I'm going to say take the sum from I equal 0 all the way out through I equal to 6, because it's the exponent that's being incremented starting at 0. And then you're going to put the square root of 2 to the I, like that. And then you could ask yourself the question, could I write this differently if I wanted to? So for example, we could write this as I equals 0 to 6. And if we have the square root of 2 to the I, this is the same as 2 to the I to the half power, so we could also write this as 2 to the I over 2 if we wanted to. So anyways, we could write this, we could put this in here as 2 to the I over 2 as an alternate form. So here's another example. So again, you want to identify what's staying constant and what's incrementing. So when I look at this particular series, I see that the 9 is constant in the denominator position for each of the terms in the series, and that this 1 right here is staying constant for each of the terms in the series. And it's this number right here that's being incremented from 1 to 2, from 2 to 3, from 3 to 4, all the way out to 14. So representing this series in sigma notation, I'd say, hey, I'm going to take the sum from I equal 1 to 14. That's where the incrementation ends. And then it's going to be the constant terms, 9 over. I have a 1 showing up in each of those terms, so it's going to be 1 plus I. And here we go, last example. So again, the idea is you need to be able to identify the pattern, and the person giving you the problem needs to give you enough information so that they think you can find what the pattern is. And of course, the problem with patterns is they're a little bit arbitrary. So sometimes there's more than one right answer. That's something to be aware of. So the less information a person's giving you, the more likely it is that you can generate more than one possibility. Usually you're going to want to try to hunt for the simplest possible case. So when I look at this particular series, they're only giving me the first term and the last term in the series. So again, the idea is to look at the first and the last term. The writer is indicating to me they think they've given me enough information to determine the pattern or ascertain the pattern. So you want to look at what's constant. So the 2 shows up in these 3 positions in the first term and shows up in the same 3 positions in the last. This n is in the denominator in both terms. This n is in the denominator in both terms, and this n is in the denominator in both terms. So the thing that's different between the first and the last term is here the 2 isn't being multiplied by anything that I can see, and here the 2 is being multiplied by an n. So what I want to do is recognize this n that I've circled here and here, or these n's are the only thing that's changed or are non-constant between the first and the last terms. So I want to look at this and say, hey, how can I rewrite this in a way that allows me to represent this in sigma notation? They haven't given me a lot of information, so I may or may not be correct. But one thing to recognize is that I could get a 2 by multiplying 2 times 1. That would still give me the 2. And this is cubed minus, here it was 2 times n. Here I'll go 2 times 1. This was 2 times n, so I'm going to choose to write 2 times 1 right here, which will change how that first term looks, but it won't change the value. And that seems like a reasonable thing to do. So I've got my 2n over n cubed minus 2n over n here. And this is times 2 over n. So I'm going to represent this using sigma notation. I'm going to say it looks like we're incrementing in these 2 positions, starting at 1 and running out through n. And it looks like it's going to be 2 times I over n quantity cubed minus 2 times I over n, close the square bracket, times the 2 over n. So again, there's kind of a paucity of information here, so I had to be a little bit creative, and the key is to focus on what's different. You know, what's different between the first term in this series and the last term in this series, and see how maybe we can adjust the first term to get something useful.